Good morning, everybody. The title of my talk is Near Field Microscopy of Bacteriorhodopsin and Conducting Polymer Bilayer Structures. The outline is as follows. I'll just give a brief introduction for Bacteriorhodopsin and the conducting polymer used, polyaniline, and also a brief introduction for near field microscopy and the technique used, and some results, and finally I'll summarize my talk. Bacteriorhodopsin is a membrane protein which is a visual analog of the visual rhodopsin. It contains a protein and a retinal chromophore. This retinal chromophore absorbs light in the green region, and this is converted into electrochemical gradient, and this is used by the protein, this is used by the bacteria to synthesize ATP in it. And upon absorption of light, there is a photocycle which is getting initiated. These are all thermally driven states, but this state is mainly due to the photo excitation, and then you have the longest lived states comprising of M's. Basically, I'll just make it into a single M. There are a lot of discrepancies here. And then this is the longest lived state which absorbs at 410 nanometers, and then it relaxes back to the ground state. The conducting polymer used is polyaniline. There are basically three types of polyanilines available: the leucoemeraldine, the pernigranilene, and the emeraldine. I am basically using the emeraldine base, which can be protonically doped to form the emeraldine salt. Hence, from the base form to the salt form gives the insulating to the conducting form. So, the previous results from our lab have shown that conducting polymers act as smart substrates for biomolecular processes, and they help and they enhance the photoelectric signals and all. And the protons from the bacteriorhodopsin are shown to dope either directly or indirectly depending on different polymers used, and these phenomena are mainly correlated to the interface related processes. So we have used big bulk films, so these are all thick solid films, and then we wanted to see what exactly happens at the interface. So to nail down the problem to interface, we need to know the behavior of each molecule and its correlation with the polymer. So, oops, there's some problem with the Microsoft. From 2007 to 2003, I'm sorry. Why single molecule spectroscopy or single molecules should be done. Basically, we all know from nanomaterials that the bulk and the single molecule or the small size, there is a property difference. The same way goes from the bulk ensemble of solids to the molecules or whatever crystals or small molecule. So we have changes from the bulk ensemble values will be completely different from what you may get in a single molecule. So in principle, you will, but for single molecule spectroscopy you can't do using, optical spectroscopy you can't do using regular microscopy, because there are lots of problems. Mainly the diffraction limit here creates a big barrier that you can't resolve objects which are lesser than lambda by 2 during distance. That comes from the radius criterion and Abbe's diffraction limit. So in 1928, Sinji proposed a good tool where he said you make a small hole which the aperture should be lesser than the wavelength of light, and then you have a detector very close to it, and then if you do a scan or something, you will be able to get very good optical images. But then further through, Hans Bethe and Buckham suggested a model in which you have a circular aperture with the diameter of the aperture being lower than the wavelength of light, and then they modeled the theory, and then they got that from the circular aperture you get both evanescent waves and propagating waves. These evanescent waves actually decay exponentially in space, so it is very difficult to get any meaningful information from these evanescent waves. The main propagating waves are all used in our normal microscopy, like ordinary optical microscopy and all the other stuff. So to get evanescent waves out, you need to have the information from the evanescent wave out, you need to have the detector very close to the